Welcome everyone to Zoom for Thought. This week we've got Cameron talking to us about polynomial identity algebras and the Kurosh problem. Take it away.
All right, yeah, thanks Sam and Vaki for putting on Zoom for Thought. So as he mentioned, we're talking about polynomial identity algebras and the Kurosh problem. If I start talking too fast, you can't understand me, let me know and I'll slow down. Or if you have any questions at any point during this talk, just stop me in the middle of it and I'll answer a question. So general outline of what we're going to do. I'm going to motivate the discussion of polynomial identity algebras by introducing the Kurosh problem. Then we'll get into some definitions of basic properties of Pi algebras. We'll look at standard identities and how they work with matrix rings. We'll then go into a pretty major result on Pi algebras called Kaplansky's theorem, and then come back to the Kurosh problem and solve a nice bounded case. So start with the Kurosh problem asks, if you have a finely generated algebraic algebra over a field, then that algebra also finite dimensional. And here an algebraic algebra is just an algebra where every element satisfies some polynomial over your field. So you can think of it as like a ring theoretic analog to the Burnside problem for groups. And just like the Burnside problem, it's false in general. In fact, Gallad showed using the Gallad-Savarez theorem that there is some infinite dimensional homomorphic image of Q with non-commuting algebra over 3 variables that is nil, meaning every element is nilpotent. So clearly, if every element is nilpotent, it's algebraic, but it's infinite dimensional. But like the Burnside problem, it's nice to consider simpler cases of the Kurosh problem, specifically like a nice bounded case. So we're going to find what it would mean for boundedness for algebraic algebras. So we call an F algebra algebraic of bounded degree over F if there's some natural number such that the minimal polynomial of an element of A over F has degree at most n. And in this case, we would call the algebra A algebraic of bounded degree n. So now we're going to state the bounded Kurosh problem. If we have a finely generated algebraic algebra of bounded degree over F, where F's a field, then is that algebra also finite dimensional? So we don't really have the tool to solve this right now, but we'll get into that by first introducing polynomial identity algebras. Some disclaimer, for me to talk, always have F be a field. Unless otherwise stated, A will be an F algebra, and the big set X will just be a countable set of non-commuting variables. So a polynomial identity algebra is an algebra A such that there's some non-zero, non-commuting polynomial such that for every homomorphism from the free algebra to A, the image of that polynomial is 0. And so you can think of these homomorphism psi as just an evaluation homomorphism. You replace each variable in every polynomial by some element of A. So this just tells us that no matter which elements of A you plug into phi, you always get back 0. And in this case, we call phi a polynomial identity for A. And so we always exclude the 0 polynomial, obviously, because that works for every algebra. So if you include that, then every algebra is a Pi algebra, and then they're not really worth talking about. So some examples of Pi algebras. So first up, commutative ones are clearly Pi algebras because they satisfy commutator. The algebra M2 of F satisfies the Wagner identity, which is just said that the square of any commutator is in the center of it. And another case is if you have a countably infinite dimensional vector space, its exterior product is also Pi algebra satisfying this iterated commutator. So some basic properties of Pi algebras. Here we're going to have a collection of Pi algebras satisfying some set of identities that might all be different. And we'll call the first one A, satisfying a specific phi. So every subalgebra of A and homomorphic image of A is also Pi algebra satisfying the same identity. If you have a finite collection of Pi algebras, then their direct product is also a Pi algebra satisfying the product of all their identities. If all your algebras satisfy the same identity, then any direct product of them is also Pi algebra satisfying that identity. One really nice fact about the identities is you can always pick a homogeneous multilinear one that still works in an identity and has degrees less than or equal to your original identity, which is nice because homogeneous multilinear polynomials have a very easy to work with form and a lot of nice properties. For instance, if you take a multilinear one, an extension of your field, then tensoring with that extension is also a Pi algebra satisfying the same identity. So these last two facts together give us that any tensor product of an algebra with a field extension, so the extension of scalars, is also a Pi algebra. So now we're going to move into standard identities. So the thing about the Kurosh problem is it's very easy to show it's going to be true over commuting algebras. And so we want to say like what kind of algebras satisfy a similar style of polynomials as just a commutator. But we want one that's bigger than just a commutator, like one that works with 3 or 4 or 5 variables. So we choose the concept of the standard identity of degree n, which is just the following alternating polynomial where big S sub n is the symmetric group on n letters. And so you can see that if you take the second degree standard identity, that's just a normal commutator. And so we can view these S sub n's as higher forms of generalized commutivity. So the question you can ask here is, do all Pi algebras satisfy some standard identity? So it's not actually true if you consider that infinite vector space is exterior algebra that we talked about before. Take any basis elements and plug them into some S sub n, you get n factorial times the product of those basis elements, which won't be 0. So only some subset of Pi algebras are going to satisfy this nice standard identity. And so let's look at some that do. So first we get our first lemma. If you have an n-dimensional vector space, a finite dimensional one, then the n+1 degree standard identity is a polynomial identity for that algebra. And so if you take some basis for some f basis for your algebra, and you take n+1 elements in your algebra, you can use the fact that the standard identities are multilinear and break this up as a linear combination of your standard identity applied to your basis vectors, some subset of them. But we'll notice that the standard identity is alternating. So if you repeat some elements, it's going to be 0. And so, in fact, because we only have n basis vectors and we have to make n+1 choices, pigeonhole principle tells us that we're going to have some repeated basis vector, and so all these terms will go to 0.
How dare you sneak in combinatorics? I thought I was done with that.
No, always sometimes combinatorics. So we get a nice corollary that every finite dimensional matrix ring is a Pi algebra over if it's over a field, specifically satisfying the n squared plus 1 degrees standard identity. But now we have a question we can ask: is there actually a smaller degree polynomial that satisfies the n by n matrices over some field that work for every field? And so we didn't use any actual property specific to matrices and their actual structure to get this identity. We just use the fact that it's finite dimensional. So you would expect that there's something better we can do. So we ask the question that if we define a function from the natural numbers to natural numbers that returns back the middle degree of a polynomial identity for your n by n matrices, what is this function f? And so that's what we're going to start exploring here. So first we're going to show that this function f would have to in fact depend on n. There's no constant number that you can get that will work for every matrix. And that's calculating this lemma that you can't pick any, should be non-zero phi, such that for every n, phi is an identity for the n by n matrices over f. So we're going to suppose this false, and we have some phi degree d that works for all of them. We're going to take the ideal generated by monomial of the degree at least d plus 1 of the free algebra. Then when you mod out by that ideal, it's clearly finite dimensional because you only have, monomial of the degree d or less, and there's only finitely many of those. So you can view the multiplication by any element of your algebra R mod m as a linear transformation from R mod n to itself. So it's a finite dimensional linear transformation. So we view it as a matrix. So we embed R mod m into a finite n by n matrix ring for some n. But then phi is not an identity for R mod m because its image in R mod m is very clearly not 0 because of degree d, which is, as we all know, less than d plus 1. And so if it's not an identity for a subalgebra, it can't be an identity for the bigger algebra. So it doesn't work. So now we're going to look to see if we can find a lower bound for our f. And we're going to show that our lower bound is going to be 2n. So to do this, we're going to take our identity, and we're going to suppose it's multilinear homogeneous, which we know we're allowed to do, and it's the degree of d less than 2n. And so we're going to re-index, our variables, and scale our phi so that there's a term of just the product of variables in order, and all the other terms of the xi's in some kind of out of order way. So then we just plug in the following like staircase of standard standard matrix basis matrices to get that all the outer order products will cancel out because we'll have some term that multiplies to 0, and then the in-order products will go to not 0. And so then phi with those with x1, x2 having all these definitions gives us just the product of x1 to xd in order, which isn't 0. And since we have d is less than 2n, we can make this choice, and so it doesn't work. So now we know d has to be at least 2n. And so now we have two bounded, upper bound of n squared plus 1. We have a lower bound of 2n. But that's a pretty big gap for large n. So can we reduce any further? And so we'll finish this up by giving a major result from Amitzer and Levitsky, which precisely answers this question. And by n matrices over a field satisfies the 2nth degree standard identity. I'm not going to prove this here because it's just very nitpicky kind of proof, but a lot of keeping track of things is kind of long. But this now gives us a nice example of the exact minimal degree. So now we're going to look back more into the structure of Pi algebras, how they work, just for what do they have to satisfy if they are Pi algebras. And we come to a major result in this field by a theorem by Kaplansky. So suppose we have a primitive Pi algebra satisfying some identity of degree d. Then the center of the field, and A is finite dimensional over a center. It's simple, and it has dimension bounded by d over 2 squared. And here, primitive algebra is just an algebra that has a faithful, simple module. So to figure this out, we're going to assume that A is multilinear because we have the tensor product by some things. So it's nice to have multilinear. So A is primitive. So by Jacobson density theorem, A is either isomorphic to a n by n matrix ring over some division algebra for some n, or we have that every finite dimensional matrix ring over that division algebra is a homomorphic image of our algebra A. But now if we consider there's the subalgebra of m sub m of d, where instead of considering d, we now just consider the center of d, z, which is the field, then that matrix algebra over field satisfies the identity of A for every possible natural number. But as we mentioned before, there's no single polynomial that works for if it's not 0. So now we get the case that A is in fact a finite dimensional matrix ring over a division algebra. So now that we got that the center of A is going to just be the center of our division algebra, it's a field, so that's one part done. And matrix rings over division algebras are simple, so that's the second part done. Now we just need to show it's finite dimensional over the center. So we're going to take a maximal subfield of our division algebra, and we're going to tensor division algebra with that subfield over its center. Now I'll make a dense ring of k linear transformations. So that just means if you have a vector space over k, you take some finite set of linearly independent vectors, and you can map that to another set, any other set of vectors in your vector space of the same like cardinality. So we consider a bigger algebra over that, where D tensor K is clearly a subalgebra of A tensor K, then that has to also be a dense ring of K linear transformations. But by our previous work, if it's a dense ring, it's got to be a finite matrix ring over K. So we get A tensor K is isomorphic to some finite matrix ring over K. And you just notice with a basic counting argument that the dimension over K is going to be m squared, but it has to be the same thing as the dimension of A over Z. And then you can bound m by the function we got before, which is 2d. And so m squared is less than or equal to the smallest integer less than d over 2 squared. So this gives a really nice structure of primitive algebras, which you then can extend to semi-simple algebras or Jacobson semi-simple algebras by using subdirect products. It just really restricts how your algebras work. So now we have this nice major result to really look when things are going to be finite dimensional, which is what we wanted to do for the Kurosh problem. So we're going to come back to it. We're going to prove a slightly more general result than what we wanted for the bounded case. We're going to show that for any finely generated algebraic Pi algebra, A is finite dimensional. So before we prove this theorem, we're going to get into a couple other ideas that'll help us along the way. So first, we're going to talk about what it means to be locally finite. So an algebra is locally finite if any finally generated subalgebra is finite dimensional. And we call an ideal locally finite if it's finally generated as a subalgebra of A. So it's a bit different than like prime ideals, which are prime if their quotient's prime. This is, we consider the ideals as subalgebras, not their quotient. So you can show a couple of nice properties of locally finite ideals. Namely, if you have a locally finite ideal such that the quotient is locally finite, then your original algebra you can lift back up and say it's locally finite. And you can use this and the second isomorphism theorem to show that we know that B mod B intersect C is going to be locally finite. So we know this quotient B plus C modulo C is also locally finite. By assumption, C was locally finite, so we lift that back up to B plus C. We get that it is locally finite. So now we know the sum of locally finite ideals is locally finite. So we can consider the sum of every single locally finite ideal living inside of our algebra. And that's clearly going to be the largest locally finite ideal because it was a bigger one, just add it to the one we have. And so we call that unique maximal locally finite ideal, the locally finite radical of our algebra. We should note L of A. And it's called radical because it works kind of like a Jacobson radical in that if you take the locally finite radical of an algebra modulo its locally finite radical, you get back 0. All right, now we can start working with this idea into proving the Kurosh problem for Pi algebras. So first, we're going to show that if we have a finely generated algebraic algebra satisfying some polynomial identity, then if you have no non-zero nilpotent elements, your locally finite radical is non-zero. And so we're going to use the following lemma, which is just a bunch of non-commutative algebra. It doesn't use anything about polynomial identities. Will just be useful for us. If you have an algebraic algebra with no nilpotent elements, then for any ideal, if you take finally many elements in your ideal, there's some idempotent in that ideal that fixes each of those elements via right multiplication. So we're going to go into prove that theorem we said before. So it's not too hard to show that the Jacobson radical of an algebraic algebra is nil. You just take the polynomial that your element satisfies over f, factor out the largest power of x in it, and then you get x to the I to some other polynomial, a non-zero constant term. That's going to be invertible because of the regularity property of Jacobson radical. And so you get your original element is nilpotent. So anyway, then A is a semi-simple or Jacobson semi-simple. So we can view it as a subdirect product of primitive rings. That just means it's a subalgebra as a product of a bunch of primitive rings such that quotient you can surject A onto any of those terms, or I guess factors of the direct product. So that just means that there exists some proper ideal P inside A that A modulo P is primitive. And so here's where we use Kaplansky's theorem to know that A modulo that ideal is going to be finite dimensional over its center. But we really want to know that A modulo P is finite dimensional over the base field of which the center is an extension. But A modulo P has also to be finally generated, and it's algebraic over F, so its center is algebraic over F. So just working out a little bit of algebra, you get that A modulo P is also going to be finite dimensional over F. So now we're going to take a generating set for A that we have because we're finally generated, and we're going to take some pullback of the basis for A modulo P, which just means that if you project all the y sub i's onto the quotient, you get a basis. So then you can work out that you can write every generating element as a linear combination of the pullbacks plus some element of P, and any product of the pullbacks as a linear combination of the other ones plus another element of P. And so we're going to consider the ideal generated by all these pullbacks, or all these extra elements we have to add on in these formulas. And we want to show that this is in fact equal to P. Clearly it's contained in it. We want to show that it's equal. And now we'll let us use the lemma to find a idempotent that fixes the entire ideal. So now we know that since the AI generate A, you can write any element of A as a linear combination of those pullbacks plus some element of Q. So now we take an element specifically in P minus that T sub P is going to be 0 modulo P, because P is in P and T sub P is in Q, which is in P. So projecting then the formula we had before gives us that we get a linear combination of the images of y sub I and the quotient is 0. But by assumption, the image of the y sub I and the quotient is a basis, so they're linearly independent. So, math 18 tells you that all these gamma sub I comma p's are equal to 0. Which is what I said here. So now we know that, P lies in Q and Q is equal to P. So as I mentioned before, now we can find that idempotent, E, we'll call it E, that fixes the UI and the UIJs via right multiplication. And you can show that any algebra with no nilpotents, all idempotents must live within the center. So we can say that then P is equal to A, the right ideal, or actually the ideal generated by E. Clearly, the ideal generated by E lies within P. And then for any element of P, P times E is going to be equal to P itself. So P is contained in an ideal as well. So since E lies in the center, it's idempotent, we can take the Pierce decomposition, where the ideal generated by E times the ideal generated by 1 minus E. And then very clearly, A modulo P is isomorphic to A times 1 minus E. But then A times 1 minus E has the same dimension of A mod P, and that's finite over F. And any finite dimensional subalgebra must clearly also be locally finite, because any finitely generate subalgebra must have dimension less than or equal to the original algebra. So we get the desired result. So now we're ready to move on to the theorem we want to tackle in the beginning of this section. If A is an algebraic Pi algebra, then A is going to be locally finite. So we're going to do it in a very standard way of how you tackle problems like this using polynomial identities. And so first, you're going to assume that you satisfy a multilinear homogeneous polynomial of degree D. I'm going to see by reduction on D, by decreasing down to a case by quotienting by something, so that we know that the term we're quotienting by is locally finite, and the quotient is locally finite to lift back up. So when D is equal to 2, either it's a commutator, or you can show that the cube of A is going to be 0. So that's the easy base case out the way. And so now we're going to reduce our problem down to something a little bit easier to work with. So we're going to pass by modding out by the locally finite radical to assume the locally finite radical of 0. And since we only care about finally generated subalgebras of A, we're just going to assume A is finally generated. And so the goal then of this proof is to show that there can't be an algebra that works like that. Can't satisfy all the properties listed here, being algebraic, Pi, 0 locally finite radical, and finally generated. So if A had no non-zero nilpotents, then we would get a contradiction immediately. So we have some non-zero nilpotent element. So we'll take some element of A that the square is 0 and consider the left ideal generated by A. We're going to take our identity, phi, and we're going to write it as a sum of two other identities. We're going to write it as a sum of psi times x1 on the left plus omega, where omega has every term of omega has x1 not in the leftmost position. So everything you can factor x1 out, we put that into factor x1 out and then put that into phi. Everything else gets put into omega. So clearly, A is in the right annihilator of T because A squared is 0. So we let x1 equal A and the xi's be in T for every I greater than or equal to 2. Clearly, omega is going to go away because you get some element of T times an element of A, which is 0. So we're just left with A times C of all those T elements equal to 0. So now we're going to consider all the elements of T that annihilate A. So clearly, that's a right ideal of T. But then since A squared is equal to 0, it is in fact an ideal of T. So T modulo W is a Pi algebra satisfying psi, since if you take any elements of T and plug them in, you'll get an element that multiplied by A on the right will give you 0. So it lies in W. So T modulo W satisfies a polynomial identity degree D minus 1, which by assumption is locally finite. Furthermore, T times W is 0, so W squared is equal to 0. So W is also going to be locally finite, since any monomial of more than 2 terms, nor in 2 factors, is going to be 0. So then we lift back up and get T is locally finite, so no radical is not equal to 0. And so then we finished this by answering the bounded Kurosh problem, which is just a restriction to the case we did before, by showing that any algebraic algebra of bounded degree is in fact a Pi algebra. And I will then give the affirmative answer using the previous theorem. So we take a algebra of bounded degree n, and we pick some element in it and take a polynomial that satisfies, which has highest order term x to the n. So we're going to commute 0, which we'll get by plugging in b into the above polynomial with some a and a to get a big polynomial in terms of commutators, the power of b's and a. But you'll notice that a sub n, alpha sub n lies in the field, so it has to be in the center. So that term just goes away when commuting by a. Now we have a only n minus 1 terms in our sum for 0. So now we're going to commute with the commuter of b and a to get now a bunch of iterated commutators in a sum. But again, alpha 1 times b comma a commutes with the commutator of b and a, so that'll give us 0 again. So now I get an alpha n minus 1. And we continue commuting with these higher and higher and higher degree terms to get rid of all those alpha I coefficients. And the alpha i's are only things dependent on b that we came in to start with. So once they're all gone, there's in fact this polynomial of iterated commutators, powers of b and a will just be an identity for a. So I showed that we get a nice identity for it. And so we get our corollary, which we're going to show if you finally generated algebraic algebra of bounded degree over f, where f's a field, then a is finite dimensional. And so this like style of proof where you take, break your polynomial up and then reduce down to a smaller case and lift that back up to your case by doing induction can be used to prove other theorems. For instance, if you have a Pi algebra where every element is nilpotent, then your algebra itself is locally nilpotent, which means any finally generated subalgebra is nilpotent. But this, my whole presentation, which went faster than I thought it would. I got a bit nervous, but just like the movie, in the movie references in the abstract, we'll end with a nice movie screen fan.
All right, let's thank the speaker. All right, does anyone have any questions for the speaker?
Yeah, so are there other, what's another typical problem in this area other than this?
Another one is, I think it's Rowan's theorem. If you had a prime Pi algebra, then you have a right. Okay, so if you have a semi-prime Pi algebra, you can show that its center is non-trivial. And then you take a prime Pi algebra and like localize at a center, and that turned out to be a finally generated central simple algebra over that fraction field of the center. So that's one other problem you can use. As I mentioned before, if you have a Pi algebra that's what we call nil, that is where every element is nilpotent, you can show that that is in fact a locally nilpotent algebra. Other problems that I've seen come up. There's another one you can use central polynomials for to show that. So if you have a Galois extension of a field, you can use the Noether-Skolem theorem to make this division algebra over it called a cross product. And for some division algebras where you have a maximal subfield that's Galois over the base field, you can get a cross product. And the question is, are all division algebras cross products? You can use central polynomials, polynomial identities to answer that question. No.
All right, cool, thank you.
All right, do we have any other questions for the speaker? All right, in that case, let's thank him again.
Thank you.
And I will now stop the recording.